Hello, Maurieo. In this video, we're going to be looking at the Travis sheet. And we've been presented with a Travis sheet here that starts at point 1 and goes to point 2, from point 2 to 3 to 4 to 5 to 6 to 7 and back to 1. So it's what we call, it's a closed loop Travis. So a point can only have one coordinate. So the thing is that we have to make sure that the coordinate of the point we started on, 1000, 1000, is where we end up when we finish. Invariably, that does not happen. We get slight errors. And this is where our adjustments come in. But first things first, we must find out the various components of each of the vectors, the northing and easting of each one. And so to do that, to work out the northing, delta north, we use the cosine. Delta north equals the cosine of the bearing times the distance, and delta E equals the sine of the bearing times the distance. Don't forget to put your remember to put your calculator into degrees mode and to convert from degrees, minutes and seconds to degrees before you find your cosine. So let's have a look at the first one, and that is minus 49.962 for the northing, and the easting is minus 13.018. Okay, so that's first one is cosine 194.3616 times 51.63, and then the easting sine of 194.3616 times 51.630. Note, the northing or the easting can never be greater than the distance. These are the components. The distance is the hypotenuse, so that's always the biggest value. Right, what I'm going to do now is I'm going to go through. I'm not going to write those all out for you. I'm going to pause the video. A few calculations later. Okay, so that's all of those in there and run out, and we've added up the columns, and we can see here that in the northing column, delta N column, we've got an excess of 13 millimeters, and in the easting column, a shortage of 7 millimeters, and that is the misclose, 13 millimeters and 7 millimeters. And what we have to do is we have to adjust that out proportional to the distance. So this here is the total distance, 144,7,654, which is just the sum of the distances here. So what we do is we go 51.630 divided by divided by 1447.654 times 0.013. That's the Bowditch adjustment there. So, and in this case here, for this particular one, and this, they must add to minus 0.013. And we just keep them to 3 decimal places. Now, we calculate each one, as I say, this one here, 0.000, and then this one here, minus 0.002. And it's very important that when we get to the end, they add up to this here, because if they don't, you'll see later on that we'll get an error, a misclose, like the start coordinate won't equal the other. Sometimes due to rounding errors, we get little problems with this, so we might have to adjust one a little bit, just a little bit up or a little bit down, so that the total equals 13. For this one here, we do it with 7, so it's still 51.63 divided by 1447654 and times 0.007. So that one's obviously going to be 0.000. So I'll halt the video and get those in, and then we'll come back. A few calculations later. Okay, so that's all those done. I have checked that they add up, so we get 2, 3, 4, 6, 7 and 6 is 13 for that one, and this one here, 1, 2, 3, 4 and 3. Now, as I said, they are proportional to the distance, so the largest correction would be in the largest line. So we've got 720 is the largest, so 6 mils in the northing minus, and 3 mils in the easting plus. The next largest line is this 207, and you see where we've got 2 here and 1 here, and 166 is the next one, and you can see that it all comes out proportional to the line, to the length of the line, and that's called the Bowditch method. Okay, which is here. Okay, Bowditch method. Right, the next thing is to work out the coordinates. So what we do here is we go, for the northing, we go 1000 minus 49.962, and then we apply the correction, which is 0 there. So for that one there, that's going to be 950.038. And then we do the next one, which is 950.038 minus 156.601 minus 0.002. And that'll give us 793.435. And now these are the adjusted coordinates for each of those points. And so on through there. And then we do the same for the easting, except for the easting, we have to add their coordinates. Add the correction. So we add the correction. These corrections are coming off. So let's get all of those in place, and then we'll come back to have a bit more discussion. A few calculations later. Okay, they're all done in there, and very important that you be honest with yourself and check that when you get exactly 1000.000. So when you come to the very last one, like 337,730. You've got to add 662.276 and then minus 0.006, and that will give you the 1,000. And it's the same with both, and that gives you the coordinates. So now we want to look at the misclose now. So the misclose that we're going to look at here is the delta N and the delta E misclose. So the delta N is, if we start from here, I always like to draw a diagram. Starting from there, we go up 0.013, and then we're going, I'm going to draw that over there a bit here. So we go up 0.013, and then we're going, so we're looking at this one here and here, and then we're going negative 0.007. Important that we get those signs right, because that gives us the vector, that there's our vector. And so we've got 0.0013 minus 0 there. So the distance is Pythagoras, which is minus 0.013 squared plus, plus 0.013 squared, but it won't matter because we're squaring it. Minus 0.007 all squared, and we take the square root of that to the half, and that will give us 0.015. So that is our distance of our misclose. Our misclose distance will be, I'll write that here, that's in the bearing column, so we can't use it. Misclose. And the distance is 0.015. Now, to work out the bearing, we can work out this angle here. We can forget about well, actually, probably be better to work out that angle there. And that angle there would be, I'll do it here, tan to the negative 1 of, and we just use the values, we don't have to worry about the signs, tan to the negative 1, 0.007 over 0.013. Now that's that angle there, and the bearing that we want, the bearing clockwise from north, is this angle here. So it's going to be, the bearing, it's going to be 360 degrees minus that tan on there, which should give you 331 degrees 41 57. And we use the little diagram to give us a direction so we know that there. So I went 13, I went from 13 up and then -7 out in the diagram here. So 13 there and there. That gave me the direction. So we can write that in here. 3, 3, 1 degrees, 41, 57. Now, for 0.015. Okay, now I wouldn't, like, the bearing should be about right to the nearest degree, because at this little small amount, you know, a little part of a millimeter can make a large amount of angle. So I wouldn't get too stressed out if you got a slightly different bearing. Anywhere from 330 to 332 would probably be okay. So that's our misclose there. Now we do have another way of expressing our misclose, and we express it as a representative fraction, and it's I'll just put it I'll put it in red so that we can see it. RF. So in this case here, RF, not RE. Okay, in this case here, it would be 1, 2. We take our total distance, 1447.654, and we divide that by 0.015, our total misclose. And in this case here, that becomes 96,510, which is pretty good. So I'll just write that here in black. Well, I'll write it in red. So that's 96,510. So looking at this, that's a pretty good Travis. Things a surveyor might say is, like when asked about the misclose, you say, 13 mils and 7 mils is one way that they might say, which is pretty good. Usually anything under 03, you know, that's 30 and 30. Anything under that's pretty good for cadastral purposes, and this is good for sort of engineering purposes. We're a bit more accurate for that. Or they might say it's 15 mils. The direction is a useful bit of information if you're trying to locate areas where you've got a large misclose, but generally that's just sort of nice to have. And then the representative fraction, 1 to 96,000 is probably what you'd say. That's pretty good. I would say typically anything over 1 to 20,000 is good. I think for some of the cadastral work, rural cadastral work, 1 to 3,000 is fine. 1 to 6,000 is pretty good. So obviously horses for courses and depends on the job. So for just a little bit of info maybe about that Bowditch adjustment there. So you to work out this one here, I'll work out this one here just to show you how that would work out. So that would be 0.015 0.13, and it's negative. It's got to be negative, and then we would multiply that by 720.402 over the total, which was 1447. So I've just included that in there because I didn't actually show a formula for it. So you'd do that for each one, so for each distance. So it's can get a little bit monotonous on the calculator. Alrighty, so that's pretty much everything that we need to do on that one sheet of paper. It gives everything on there a pretty quick sort of thing there. So yeah, that's Travis sheet 1 all worked through, and there it is in a nutshell. A lot of information in a bit of a form there. I've added little bits and pieces. The diagram, I think, is most important. The main thing to remember is that the Travis must close. It must close. So when you calculate your Bowditch corrections, check that the rounded corrections add up properly. So sometimes these might not add up to 12, so you've got to do a little bit of guesstimating or pick a favourite. But remember that the longest, the biggest correction goes into the longest line, and otherwise, and they cancel out the misclose, so that's important. The final coordinate should come back to the starting coordinate. In this case, a point can only have one coordinate, one height. Right, so that's key there. If this helped, give the video a like and, subscribe. It helps the algorithm know this sort of thing is useful. And if you're still getting stuck, put a comment below. Let me know which part is causing the problem, whether it's the bearings, the delta N, delta E, the Bowditch correction, or the final coordinates, or the misclose. And I'll try to cover it in another video, or I'll focus on that particular sort of thing in the next one. All good. Cheers. Bloody marvellous.